In this tutorial, we're going to look at electric field intensity as it applies to two interesting phenomena, some of which we're familiar with. Another one we have a very common misconception about. The two topics I want to talk about are sparking, whether it be lightning bolts or little sparks that we saw in class when you get close to the generator. The second one is associated with being in let's say a car and being hit by lightning. And most of us understand that we're kind of protected if we're in a car, but we're not necessarily sure why. Spoiler alert, it's not because of the rubber tires. It's something else entirely different. So I want to establish those and show you two little quick YouTube clips to illustrate. And then when we come to class, I'll address questions and I'll maybe show you some other things to bring it home. Okay, so let's start with sparking. I'm not going to show you now, but I can describe it, and we can certainly see it in class. I charge up the static generator. We know we can get shocked if we touch it directly. But if you paid attention to the multiple times that I shocked myself, a number of times I would get shocked when my finger or hand was a certain distance away from the static generator. In other words, there was a spark between us, a little miniature lightning bolt. So I never explained why that occurred, because it's actually a fairly complex concept, but I'll simplify it a little bit. And this is definitely important when it comes to lightning strikes, because lightning is a large spark, generally between a cloud and something on the ground. So we want to understand, well, why does it happen? Okay, so very simply, we can boil it down to this: when the electric field intensity between a field charge, let's say a cloud in a lightning storm, and a test object, let's say a tree, exceeds a certain amount. That amount, when it's air that's between the object and the source of the charge, is 3 times 10 to the 6th newtons per coulomb. So when you exceed a field that's 3 million newtons per coulomb, air will break down. Okay? And so I want to explain that breakdown idea a little bit more, and a spark will result. Okay? So breakdown is not necessarily separate the atoms that make up the molecules of air, being nitrogen or oxygen. It's more that it ionizes it. All right? So you've heard that term ionize before in chemistry. And that all it means is it strips off electrons so that what remains is a charged ion. So imagine this. We have a cloud. You don't have to draw this, right? Here is some object on the ground. It could be a person, it could be a tree, and you have air between them. And the air is a very good insulator, so all the charges that build up on a cloud shouldn't jump to the person. But because the air is made up of a material, and that material has positive and negative charges in it, it's the neutral atoms that make up the air, if this field generated by the cloud is really, really, really high, and there's a few ways that can happen, then the negatives from this charge are stripped off, and we create a conducting path for the field charges to get to the object, and then you have a quick transfer of energy and charge. In other words, you have a spark. So what if you want to increase the likeliness of this, which is something you want to do, let's say, for a spark plug in an engine, or you want to decrease the likeliness of this for, let's say, a lightning strike? In other words, what factors determine whether the likeliness of a spark or not? Okay? The most obvious thing to do is increase the charge of the object. Right? The more charge you pile on to a sphere, the greater the field's going to be, because we know that E is proportional to the amount of charge. Okay? So that's pretty straightforward. However, that doesn't explain necessarily why my hand or finger will create a spark when I approach it from a certain distance. The amount of charge on a sphere is at its maximum. It's not building up more and more and more. Okay? So this, what I'm about to say, should make sense in hindsight, but you may never have realized it. Or you can enhance the electric field by making either object pointy. Yeah. Okay? You shape it into a sharp point, or if you're talking about lightning outside, that's generally the tallest thing in the field. It could be a tree, it could be a building, it could be a person. So if you don't want to get shocked by a spark, you generally make yourself as round as possible. So if you think about situations where you do want sparks, let's say a lightning rod, you want to attract the lightning towards the rod and rather than a building, you make it pointy. In a spark plug, you have a little pointy part that's going to enhance the likeliness of a spark. So if we look at, I have some generic pointy object here. If we look at the charge distribution, let's say this is negatively charged, what you will find is the charges want to spread themselves out as much as possible, but at a pointy part, they really pile up because of the geometry. So on the square part, the flat parts, we have a low electric field, but at the pointy part, we have a very high electric field. So a spark is most likely to occur there when you bring another object close enough to it. But long story short, the spark only occurs when the electric field exceeds that amount. All right? Next thing I talked about is why someone is protected from lightning when in a car. All right, it's not foolproof, but you're not going to get shocked when it. And this also applies to being in an airplane. If you've ever flown an airplane and an airplane gets hit by a lightning bolt and it doesn't catch fire, you're not going to get electrocuted, even if the airplane fuselage is made up of iron or some metal. Same with a boat. If you're in a boat and the water gets hit by lightning, and you're on the inside of the boat, and let's say it's a metal shell, you're not going to get electrocuted. If you're on the outside and touch it, then you're in trouble. So we're going to see that when you're inside a metal cage, ironically enough, you are protected from electric fields. When you're outside it, you are not protected. So when I ask why is someone protected when in a car, you ask the general public, I would say 9 times out of 10 people say something along the effects of rubber tires. Okay? And as I mentioned earlier in this, I said, no, this has absolutely nothing to do with it. If you were on a motorcycle and got hit by lightning, you would be in big trouble. And it does have rubber tires. If you're in a boat, which doesn't have rubber tires, you're relatively protected. Okay? So what's going on is something called the skin effect. This has a wide applications in many, many areas. I just want you to be aware of the key point, which I'll point out in a minute. Okay, so here is the idea. Let's take a hollow sphere as represented by, and let's say you're inside of it. Okay, then it becomes charged. Well, where does the charge want to go? Well, it wants to go to the outside of the sphere because the charges want to get as far away from each other as possible. So let's say this is some sort of, a plane, a boat, a car, and you touch the inside of this somehow or another. It doesn't matter with what, a hand, a foot, or some extension of a wire or whatever. You might think I'd get shocked by touching that charged object, but you will not get shocked by that because in order to get shocked, all those red charges would have to come closer together to shock you. And they don't want to come closer together. They want to get as far apart as possible. So you're protected in there. And a way of quantifying that is, and this is the most important takeaway from this, is no matter where you are inside a metal conductor, okay? I'll take that back. Sorry. A hollow conductor. And actually, I'll change my mind on that. You're probably really mad at me right now. Inside a conductor, it doesn't have to be hollow. It kind of have to be the inside of it. But even a solid sphere, this rule applies. And if it's a conductor, then it's probably made of a metal. That's why I changed my mind. But anywhere inside a conductor, the electric field intensity is 0. Okay, that's a really, really important point. So metal shells are very, very useful for shielding from charge. A lot of applications to this, especially in the electronics industry. So I'm going to show you 2 pretty cool examples of this. One is a car strike. So let me see if this link works. Okay, I'm not going to play the audio because it's really not audio. So there's just some car going along. And wait for it. Boom. People inside realize they just got hit by lightning. And if you could hear the audio, maybe kind of if you turn it up on yours, you will find that they're screaming, shouting, but they're still alive. They did not get harmed by this. Okay? The other video I want to show you, let me see if I can get back to